like to look at is we like to look at the finding volumes of a solid with known cross sections. So we're going to be looking at a few questions together and then see how we can find those volumes. So now first is y equals square root of x, where x goes from 0 to 4, and given that the known cross section is the square. Now let me attempt to try to sketch this one for you. And then here our graph would have been look something like this. Now imagine this is 4. Now what we're looking at is if the cross section is a square, then we have a parallel squares perpendicular to the x-axis. That's what we're assuming. I forgot to mention that. Perpendicular to the x-axis. Now, then imagine, let me try to draw the 3D picture here. See, we have a bunch of squares. Where one side is on that xy plane, and then we have a bunch of other. So then we have a bunch of squares which come together, which forming a particular solid. Now, the one thing about the solid is that a cross section is always squares. So in that case, how do you find the volume? In fact, very similar to before, what we have done before was that we gathered a whole bunch of thin circles or thin cylinders. In this case, we are gathering a bunch of square-based pyramid, very, very, very thin ones. Then, how do you find the volume of each one? Volume of this, pyramid is basically base area, which is side square times the thickness. But in this case, it's cutting the x-axis, so we have dx. But what is the length of a side? Length of side is the y value here. So in fact, this is the same thing as y square dx. But y in terms of x is square root of x quantity squared dx. So therefore, when you collect all of them, then we get integral sign of square root of x squared dx, which goes from 0 to 4. That's basically what we end up getting. So if I have to rewrite this one, I'll be getting 0 to 4 for x dx. Now, rest of them is mere calculation. Here we get x squared over 2. That goes from 0 to 4. Obviously, when you plug in 0, everything becomes 0. So when you plug in 4, we get 4 squared over 2, which is equal to 8. So 8 will be the volume of that such solid. But then, are we going to have square as a cross section all the time? No, not necessarily. We have a couple more examples. Number 2. So I have a linear function, y equals 4 minus 2x from 0 to 2. And then, in this case, cross section is a semicircle, once again perpendicular to the x-axis. Now, then let me try to sketch this one more time. So here we get 4 minus 2x. The graph would have looked something like this. Now, but each cross section perpendicular to the x-axis is a square. I mean the semicircle. So I have this can be my diameter. That can be my diameter. You can see that trying to give you the picture, but so everything it almost looks like a cone, half of a cone it looks like. But what we need to do is we need to it's a prism in a way that base area is the semicircle, and the thickness is the height. So then, how do you find the base area? It'll be pi r squared, which would be circle, but we have to divide that by 2 times the something. Now, then we get pi over 2. But what's the value of r? You see, from here to here is the diameter of the circle, which is equal to y value. So radius in this case is equal to y over 2. So therefore, what I can do is y over 2 quantity square dx, because everything is cutting against the x-axis, and 0 through 2 because that was a boundary. If I have to rewrite this one, then what do I end up getting? Pi over 2 can be comes to the front, 0 through 2. In place of y, we have this one. So we get 4 minus 2x divided whole thing by 2 quantity squared dx. Then we get pi over 2 integral of 0 through 2, and then we get 2 minus x dx. And we can easily do this one. So we get pi over 2, 2x minus x squared over 2, 0 through 2. Of course, when you plug in 0, nothing will come out. But when you plug in 2, this one is what? 4. And then this one is 2. So 4 minus 2 becomes what? 2. So pi over 2 times 2, which we get pi itself. Alrighty, let's look at the next question. Now we have two equations, and the intersection section enclosed by those two will be our region, and cross section is equilateral triangle perpendicular to the x-axis. So let's try to look at this one together. And then I'm going to assume that y equals x. And then y equals x squared. So we know that that's the area. But equilateral triangle is perpendicular to the x-axis. So then I know that each triangle would have looked something like this. That's the base, that's the height, that's the base, that's the height, so forth and so on. And you collect all those things. Just out of curiosity, what's the area formula for the equilateral triangle? It's radical 3 over 4 side square. So what is the side? Side, in fact, is the difference between those two graphs, the blue one and then the red one. So we on an intersection, we can easily see that it's got to be 1, 1. So we, since rectangles are being cut, or the triangles are cut against the x-axis, so we're going to go for x boundary, which is 0 through 1. And then radical 3 over 2, or radical 3 over 4 can be outside. And what is the length of one side of each triangle? It's the blue one, which is x minus x squared quantity squared dx. So then what do we have? Radical 3 over 4. This one, if I have to rewrite it, this one squared becomes what? X squared minus 2x cubed plus x to the 4th power dx. Now, then we are ready to get the integral. Radical 3 over 4. And what do we have? X to the 3rd power over 3 minus 2x to the 4th power over 4 plus x to the 5th power over 5. That goes from 0 to the 1. Of course, when you plug in 0, everything becomes 0. Now, but if you have to plug in 1, everything only has the, what do you call that? Coefficients left. So radical 3 over 4. So I have 1/3 minus 1/2 plus 1/5. I can make the denominator of 30. So then we get radical 3 over 4. So we have 10 minus 15 plus 6 over 30. That's what we can do. And then here we get, that's 1 over 30. So our final answer is radical 3 over 120 becomes your final answer. All right. With this one, I'm going to close up for today. See you later.